can let him in if you want. Hey guys, welcome back. Give me just 1 second. We'll get moving. Hang out with Papa. You gotta be good. Daddy's working. All right. So welcome back to college algebra. Last time we talked about methods for solving systems of equations, and today we're going to talk more about systems, but not systems of equations, systems of inequalities, which are different but similar in spirit. Before we do that, I want to talk a little bit about class structure, some announcements, things like that. So let's go ahead and turn on the screen share, get the dot camera firing. Yeah, now you want out. That's what I thought. That's what I thought, Max. Yes, you're cool. Yes, I love you. What's wrong, buddy? I can't play it. So this is MAC 1105 section 015, which is a college algebra class. And the date today is the 14th of April, 2022. The name of the game today is Systems of Inequalities. Now, before we get into that, I just want to let you know that homework 20 and quiz 20, I went ahead and extended those to next Thursday. I don't see any harm in leaving those open until the last day of class. I know a lot of us are working to catch up, busy in other classes, things like that. So the idea of trying to like crunch you class to class to make sure you're doing that homework, it's less important now at the end of the semester than it is at the beginning of the term. So homework and quiz 20 have been extended to next Thursday, which is 4/21. Other stuff. So exam 3, remember the last midterm exam, exam 3 is approaching. It's going to be on that Thursday. Remind me, did we decide, did we take a poll or anything like that? I remember I took polls in one of my other classes. I don't remember if I did it with you guys for the date of exam 3, or did we just say it's going to be on the 21st? We just said for this class it was going to be on the 21st, right? I don't think we've set it here. 6, that's the last day. Yeah, okay. Well, maybe it's worth going ahead and taking a poll. Let me go ahead and do that. So basically, today we're going to talk about systems of inequalities, which is the last bit of new material in the class. So if you guys want, we have a choice here. We could have the exam next Tuesday, which would mean the test is coming a little sooner. You have a little bit less time to prepare. And then we could use next Thursday as a day to review and study for the final, right? We could have like a final exam review day on Thursday if you want. So the first choice here, I'll have the other choice would be next Tuesday, 4/19. Okay. So I'm going to go ahead and launch this poll. You're going to have two choices. You can tell me if you want the exam next Thursday, which is the last day that we meet. And that would mean that there's no dedicated review day for the final, but you get a little bit longer to study for exam 3. Or we could have the exam next Tuesday, which is the 19th, which means next Thursday, our last day of class, will be dedicated to reviewing for the final. I'm going to go ahead and launch the poll. Let me know what you want to do. I don't have a bias one way or the other. Think about what would be best for you. Oh, yes, you're very cute. Oh, yeah. Still got 5 people I'm waiting for. Four people left. Ooh, and I think with that vote, choice 1 wins. Yeah. So even if all 3 people went for the 19th, that wouldn't be enough to turn the tide. So I'm going to go ahead and end the voting here. These are the results. So exam 3, the last midterm exam, is going to be next Thursday, which means we won't have a dedicated day to review for the final in class. Now, Santa Fe, it is not uncommon for Santa Fe to do a big final exam review, although I haven't heard anything about that this semester yet. That is what we're going to do. So exam 3 is next Thursday. And it will be in class, proctored, the same way we have been by Honor Lock and Zoom. The last thing I want to put under this announcement heading is the date of the final. I know I've been hammering on this, but I want to make sure that we are all on the same page. So your final exam, if you look at the syllabus, your final exam is going to be on the 26th at 10:30 in the morning. If you haven't put this in your calendar, please do so. Make sure you set an alarm, make sure you set a few notifications. What's the day of the week there? Tuesday, what is that here? Tuesday? Yeah, Tuesday, 4/26. This will be run the same way our other tests are. It's going to be set up in My Open Math. It's going to be proctored by Honor Lock and Zoom. The only difference is, of course, the final is cumulative. It will be a little bit longer. It's a 2-hour test, but the structure and the rules and all of that are the same. So this is our roadmap for the end of the semester. This is what we're doing, right? Your last homework is going to be extended to the last day of class, which for us is the 21st. It's the date of exam 3. I'm going to have your most recent homework, the one that we're going to talk about today on systems of inequalities, be due on that same day. That way you can kind of pace yourself and put time into we're prepping for the final or doing whatever else you need to do between now and that last day of class. On the last day of class, we're going to have exam 3. It's going to be run the same way as all of our other midterms. It's going to cover all the material that we've talked about since exam 2. So that's going to be exponentials, logarithms, and systems, both systems of equations and systems of inequalities. And then you'll have a few days off between the midterm exam and the final exam, which is going to be on the 26th. You'll have a total of 5 days for that. So between the midterm here on the last day of class and the final, you definitely want to be putting a few hours into studying for this stuff every single day. You want to go back through all of the activities. You want to go back through any homeworks that you haven't finished or any homeworks that you don't feel 100% confident on. There is a final exam review packet. Let me see, did I post this for you guys? Maybe, maybe not. No, okay, let me go ahead and do that now before I forget then. The only catch is that this review packet was put together when we were doing the final in Pearson. So the final in My Open Math might be structured slightly different, but the same type of questions will be on here. Final exam review materials, questions and solutions. Here we go. All right. All right. So I think that knocks out all the bookkeepy stuff. Moving into the actual mathematics for today, I would be open to taking questions from the homework set, that was originally due today on systems of equations. Is there anything that you guys want to see from homework 20? Anything that was giving you a hard time or you'd like to talk about a little bit more? Anything at all like that? Feel free to shout out or post in chat. Okay, well, if anything comes to mind, again, don't hesitate to shout out. The material for today is systems of inequalities.
Could you do 28 by chance?
Sure. Okay, yeah, let me set this off to the side. You said 28?
Yes.
Yeah, let's take a peek. It's always nice to.
Yeah, I was about to say the same thing.
Okay, why not? I was surprised when I came in here was seeing the differences between this and the Pearson version. So it seems like when you run into a system with infinitely many solutions, the MyOpenMath platform isn't asking you to characterize them, which yeah, was surprising to me because we've always required that of college algebra students. But it looks like you might be off the hook as far as this homework is concerned now. Solve the following system of equations. The solution with a more negative x is this. The other possibly repeated solution is this. All right, let's write it down. This is homework 20, number 28. And we just want to solve the system 2x squared minus 2x plus y equals 2 and negative y plus 5x equals 0. They don't specify a method, but it is what kind of system? Think of the classification schemes we talked about last time.
Nonlinear.
Excellent. This is a nonlinear system because the first equation is quadratic in the variable x. There's an x squared. So of the two methods we have, which one should we employ?
Substitution.
Yeah, substitution is the more general path here. Now, looking at this, this may or may not have jumped out at you. You could actually eliminate here as well. This is rare for nonlinear systems, but because the coefficient of y here is +1, and that's the only instance of y, the coefficient of y here is -1, and that's the only instance of y, we actually could eliminate in this system. But let's go ahead and follow our guidelines and see what we get, because it's going to yield the same thing and it'll come very quickly. So we're going to solve, this is nonlinear. And in general, that means we're going to use substitution. It's very rare to encounter a nonlinear system you can solve by elimination. This happens to be one of them. But if I solve equation 2 for y, which I can do by adding y to both sides here, then I get 5x equals y. And then I can back substitute that, or not back substitute, but I can substitute that in here. I can plug y equals 5x into equation 1. That's going to give me 2x squared minus 2x plus, I'll write it all out. So if I take 2x squared minus 2x plus y equals 2, and I plug in 5x for y here, that's going to give me 2x squared minus 2x plus 5x equals 2. So this is what we get from performing the substitution. And then our third step was to go ahead and solve that equation. So I'm going to write 2x squared minus 2x plus 5x equals 2 is equivalent to, all right, help me out. How do I solve this equation?
Pythagorean theorem.
Maybe that's just a naming thing more than anything else. Pythagoras won't necessarily help us here. At least I don't see it right away. That's the a squared plus b squared equals c squared thing from a right triangle. But we could use the quadratic formula if we must.
That's what I meant.
I have a feeling. Yeah, okay, it's okay. Before I dive into that, though, there's a couple steps that I'd like to perform. So before I could apply, I can't like jump in with the quadratic formula right away here. And there's some stuff we could do to see if we could solve this faster, right? Like factoring or stuff like that. So let's begin by putting these two pieces together. These are like terms. And let's also pull the 2 over to the left-hand side, because whatever we're going to do, factoring, quadratic formula, we need the quadratic set to 0. So 2x squared, and then minus 2x plus 5x is plus 3x. And then I can also subtract this 2 over, minus 2 equals 0. So this quadratic here is equivalent to this quadratic here. This one is in a much better position to solve. If I want to solve this quadratic without the formula, without the quadratic formula, I would need to factor it. And factoring here would require the AC method. So I'd take this number A and this number C, let me just write this down, AC here, and we multiply them. So that's 2 times negative 2, which is negative 4. B is 3. So I'd be looking for 2 numbers that multiply to negative 4 and add up to positive 3. I think this might be factorable. Can anybody suggest 2 such numbers?
Or -1.
Yeah, excellent. So that means I'm going to rewrite the middle term here, the 3x, as plus 4x minus 1x. So that's 2x squared plus 4x minus 1x minus 2 equals 0. You guys remember this? This is the AC method for factoring quadratics. It's the tool we need to factor these when the lead coefficient isn't 1. Then we factor by grouping. So I look at these 2 pieces separately. I pull out the GCF from each, and what's left over should match. So from that first piece, the greatest common factor, the GCF, is 2x. And what would be left is x plus 2. from the second piece here, the greatest common factor is just -1. So I have -1 times, and then what's left over is x plus 2. And the purpose of splitting this 3x into 4x minus 1x is that when we pull out the GCF from each of these, the x plus 2 is common to both. So finally, if I extract that x plus 2 factor, this piece will just give me a 2x, and this piece will give me a -1. So here is the factored form of this quadratic, 2x minus 1 times x plus 2. So no quadratic formula needed. Although it would work, just more time consuming. Each one of these gives me an x value. If I set this guy equal to 0, I'll get x equals 1/2. If I set this guy equal to 0, I'll get x equals -2. And now I back substitute each of those into either original equation. For my money, the second guy is the simpler. So let's do that. So we have two solutions. On the one hand, if x is 1/2, then we have -y plus 5x equals 0, means -y plus 5 times 1/2 equals 0. And adding y to both sides, right, 5 times 1/2, that's 5/2 equals y. So the first solution is the ordered pair 1/2, comma 5/2, or x equals 1/2, y equals 5/2, however you want to say it. That's the first solution to the system. The other solution comes from x equals -2. I'm going to draw a little partition here. If x equals -2, same deal, plug back into the simple equation, -y plus 5x equals 0. This will become -y plus 5 times -2. Oh, this pen is dying, sorry. Equals 0. This says -y minus 10 equals 0. And again, you can add y to both sides. So -10 equals y. That means that our second solution is the ordered pair -2, comma -10. And this would be the x, this is the y. That's it. Okay. So seeing this all here, do we have any questions about how we solve this system? Oh, Max, okay. Just for fun, let's take a look at the graphs. First equation was 2x squared minus 2x plus y equals 2. Second equation was -y plus 5x equals 0. Let me scale the y-axis a little bit. This. And you see the two solutions here. And 1/2, of course, is 0.5, and 5/2 is 2.5. Okay. Nonlinear systems. They can be hairy, but the ones that you're going to see, they're not going to be too bad, right? This is about as bad as that's the nonlinear systems you'll encounter will get. Last call for questions on what we did here. Okay, great. Let's talk about systems of inequalities. A single inequality in two variables doesn't have a solution that you can write down very neatly, and neither do systems of inequalities in two or more variables. It's not something that you can write an algebraic solution for in any particularly clean sense in general. In fact, the most convenient way to express the solution to a system of inequalities is usually to just write the system of inequalities. The only other way to express the solution is to sketch it, and they're going to be regions in the plane. So to give you a feel for these, I want to look at some very, very simple ones to try and get you comfortable with the notation and how the things look, and then we'll look at some homework level examples. So these are collections of inequalities meant to be solved simultaneously. All right, just replace the word equation with inequality, and you get the definition for a system of inequalities. Nothing special there. The solutions to these are regions in the XY plane. Right, so an individual solution is going to be an ordered pair, just like for a system of equations. But the full solution set is going to be these large collections of ordered pairs, and geometrically they form regions in the plane. So I think it's best to just start by looking at some very simple examples, like let's look at the single inequality. X is greater than 0. So if I'm thinking thinking of this as a system, then the solution is all ordered pairs x comma y such that x is greater than 0. I know that doesn't seem exciting, but it's the truth. So some examples of points that would solve this would definitely be like 1 comma 0. Right there, x is 1 and y is 0, so x is greater than 0. The point 2 comma 3 would be a solution. And the point 0.2 comma -2 would be a solution. The point 1 comma 3 would be a solution. Any point whose x coordinate is positive would be a solution. And if you want to look at all of these all at once, that's everything to the right of the y-axis. This whole region, if we want to use the language of quadrants, we could say quadrant 1 and quadrant 4 solve the inequality. If you take any point from the left half plane, any point over here, the x value is going to be negative. So that does not satisfy this condition. Nothing crazy, right? I'm going to look at one more kind of very simple inequality like this, simple system of inequalities, and then we'll generalize. So let's solve the inequality x is less than 1 and y is greater than -2. And sketch the solution. In the plane. All right. So the trick to this, and this is going to be basically the same thing that we're doing for all of these, you want to figure out the boundary for each of these inequalities, right? Each of these inequalities is going to do the same thing that this one did. It's going to chop the plane up into two spaces, into two regions. And we want to find the overlap of the region that solves this with the region that solves this. Okay. The general thing to do here is you ask yourself, what does the line x equals 1 look like? Well, it's x equals a constant, so it's a vertical line going through the point 1, 0. So, okay, here's a point where x is equal to 1. And the line x equals 1 is this vertical line. Now I'm going to draw it in dotted. Because points which are on this line do not satisfy the inequality x is less than 1. Right? Think about the point 1, 0. If you plug 1 in for x here, do you get a true statement? Is 1 less than 1? No. And the same is true of the point 1, 1, 1, 2, 1, -1. None of the points on this line solve the system, so we draw it dotted. We draw it dashed. And this is the convention. If this was a less than or equal to 1, then I would draw the line solid, indicating that the points on the line are a part of the solution set. So the solution set to the first inequality, x is less than 1, is either going to be the right half of the plane or the left half of the plane divided by this vertical line, x equals 1. Which one is it? Is it all the stuff to the right or all the stuff to the left?
Everything to the left.
Very good, everything to the left, right? I want the x value to be smaller than 1. So like x equals 0 would work. So the point like 0, comma 1 would work. The point -2, comma 0 would work. So what I'm going to do is shade everything over here. Show a little more densely than that. Now we do the same thing with the other inequality. I'm going to use a different color here. So the line y equals -2 this is y equals a constant, or you can think of it like m is 0. So this is a horizontal line. Through the point 0, comma -2. Okay, well, here's 0, -1, here's 0, -2. So we're looking at a horizontal line. Here. Same idea. The points that are on this line do not satisfy that inequality. The inequality y is greater than -2, because the points on this line have y value exactly equal to -2. And now we're asking for y to be larger than -2. That means I'm looking at all of the points which are above this line. The solution to your inequality is the overlap. So sort of this region in here is the solution to your inequality. So the stuff that's shaded in purple solves the first inequality. The stuff that's shaded in dark blue solves the second inequality. And the stuff which solves both, the overlap to those two solution sets, is the solution to the system. Make sense? Now this obviously is a little bit cluttered. So moving forwards, I'm not going to shade the whole region for both. We're just going to talk about the different regions in the plane, and I'll shade only the solution set to the whole system. But I want to do these kind of simple examples to make sure we're really comfy with what's going on. Any questions about either of these examples? Questions about either of these? So again, what we did here is we looked one inequality at a time. We sketched the line that forms the boundary for that inequality. So if you have x less than 1, you sketch the line x equals 1. If you have the inequality y is greater than -2, you sketch the line y equals -2. That chops the plane up into different regions. The overlap of the two solution regions is the solution to the system. Let's try something a little harder. How about That's, oops, sorry. Not a system of equations. We want a system of inequalities. So let me make this greater than or equal to, and I'll make this strictly less than. So I need to figure out what each of these look like kind of as a line. I want to take each of these and sketch the two lines. Two x minus 4y equals 12. And a different color. X plus y equals -3. So to sketch each of those lines, I think it's nice to solve them for y. If I solve this guy for y, let me see, 2x minus 4y equals 12 is the same as -4y equals 12 minus 2x. And then dividing both sides by -4, I get y equals -3 and then plus 1/2 x. So this is a line whose y-intercept is -3 and whose slope is +1/2. Let me go down here, 1, 2, 3. And the slope being +1/2 means we're going to hit the x-axis at 6. So 1, 2, 3, 4, 5, 6. We know how to graph lines at this point. When I draw this line, I'm going to draw it solid because the points that are on this line are points that solve this equation. And this is a greater than or equal to. So if 2x minus 4y is equal to 12, then the point x comma y is a part of the solution set to this inequality. So the basic idea is if you have a greater than or equal to, or a less than or equal to, you should draw the line solid. If you have a strictly less than or strictly greater than, you should draw the line dotted. So here's my y-intercept, here's my x-intercept. Those 2 points are enough for me to draw a nice picture of this line. Here it is. There's the boundary to the first inequality. I'm going to do the same thing with the second guy. I take x plus y equals -3. That's the same as saying y equals -3 minus x. So this is a line with y-intercept -3 again, but now slope -1. Let me come over here. When x is -3, y will be 0. So my x-intercept is here, my y-intercept is here. This one I will draw dashed because that is a strict inequality. Right, not less than or equal to, but less than. So what you see is this chops the plane up into 4 regions. There's a region up here, there's a region over here, there's a region down here, and there's a region over here. One of these will be our solution. The other 3 will not. Handful of ways you can do this. Once you have these 2 plotted, the dashed and solid as they ought to be, you can think about testing points from each of those regions. So you can take a point that is in the first region, plug it into the system, see if you get a true statement or not. If you do get a true statement, then that whole region is the solution. If you don't get a true statement, then no point in that region is a solution. And you can do that for each of these regions. What I find students generally prefer, though, is to think about each of these as being like above or below. Let's do the test point thing first, because it is the more rigorous way to do things. So we're going to test a point from each region. Let me call this region 1. Call this region 2. Call this region 3. I'll call this region 4. So a point that is in region 1 is 0, 0. So if I plug 0 in for x and 0 in for y, do I get a true statement? The first inequality would say 2 times 0 minus 4 times 0 is greater than or equal to 12. And the second inequality would say just 0 plus 0 is less than -3. Neither of these are true, right? The first one says 0 is greater than or equal to 12. That's not true. And the second one says 0 is less than -3. That's also not true. And we would need both of these to be true for this point to be a part of the solution. So region 1 is not a part of the solution set. We can test a point from region 2. So I need a point that I know is over here. Can anybody suggest a point? Remember, this is -3, and this is also -3, so 6.
-4, 2, or -4, -2.
Yeah, I think -4, 2 could be up here, could be right on this line. It's not immediately obvious to me that that one is going to be -4, -2. That looks good. Yeah, that's right here. Other reasonable choices would be like -3, -2, or the y value here, -3. That's the first thing that comes to mind. These guys meet when y is -3. So if I were to do something like -1 or -2, -3, just going to the left from this, I know that's going to be in here. We can test either one of these. Let me say, what did we say? We said -4. Actually, -4, 0 would be a good choice also, right? -4, 0 is right there. But we can do -4, -2. So that would be this point. And if I want to test that guy in the first inequality, I'll get 2 times the x value there is -4. So 2 times -4 minus 4 times -2 is greater than or equal to 12. And the second inequality would say -4 plus -2 is less than -3. So if both of these are true, then this region is our solution region. 2 times -4 is -8. minus, let's see what we have here, -8 minus -8. Oh, interesting. So is this true? Sure, Sam, yeah, that's fine.
No.
No, it's not, right? -8 minus -8, that's 0. And 0 is not greater than or equal to 12. The other guy, though, if I take -4 plus -2, that'll give me -6 is less than -3. This is true. So region 2 solves the second inequality, but does not solve the first inequality. Now remember, we need the system to satisfy both inequalities at the same time. So region 2 is not a part of the solution set. All right. So we've checked regions 1 and 2. Let's check region 3. Any questions on the work we did here before I move on? Are we all comfortable with what we're doing here? Why? Okay, let's try region 3. If I look directly below this at 0, -4, that's definitely a point that is in region 3. So let's test 0, -4. That would mean 2 times 0 minus 4 times -4 is greater than or equal to 12. That's the first inequality. And the second inequality would say 0 plus -4 is less than -3. Well, this first guy says 0 minus -16, which is +16, is greater than or equal to 12. That is true. And the second guy says just -4 is less than -3. That's also true. So region 3 is our solution region. And we can check region 4 to see if that's also a part of the solution. With these linear systems of inequalities, you won't encounter something like that. Once you find your solution region, you're done. But just for shits and giggles, I could take a point to the right of this point, something like 1 or 2, -3. Let's do 2, -3. If I plug that into my system, I have 2 times 2 minus 4 times -3 is greater than or equal to 12. And the second inequality there, we would have just 2 plus -3 is less than -3. And this would say 4 plus 12 is greater than 12. This guy would say 2 minus 3 is less than -3. So the first guy is true. This again says 16 is greater than or equal to 12. The second guy is not. This says 2 minus 6, it's -1 is less than -3. That's not true. So region 4 doesn't solve. Okay. I'm writing out every little thing here. And as you solve these, you don't necessarily need to write out every little thing. So you could make this go a bit faster, but the end of the day, the result is that this is your solution region, right? Everything that is sort of beneath both of those lines. Okay, and this region extends forever and ever like this, and down forever and ever as long as we stay under this guy and under the other guy. And there really is no clean way to describe this in terms of algebra besides the original system. The original system is sort of the nicest way to describe this. But there is a faster way to identify the solution region. You just have to be a little bit careful. So I'm going to set up another system here, and I'm going to ask you guys to walk me through sketching the lines, and then we will see that faster way to identify the solution. So let me go ahead and take one from your homework. So plenty of straightforward inequalities like this. Let's take a look at number 3. Sketch the system. Y is less than 1/2 x plus 2. And y is greater than negative 2x minus 1. This is already in the form that is sort of most convenient for the faster method I'm going to describe, but we still need to go through the process that we began with last time, where we graph the two lines. These inequalities have already been solved for y, which makes them nice to work with. So we're going to begin by sketching the lines y equals 1/2 x plus 2 and y equals negative 2x minus 1. So the first guy, this is a line with y-intercept 2 and slope positive 1/2. We'll go 1, 2. If the slope is positive 1/2, that means my x-intercept would be over here at negative 4, 0. Should I sketch this line dashed or solid, and why?
Dash because it's not a greater than or equal to sign.
Very good. I've got a strict inequality here, right? This is strictly less than, not less than or equal to. So when I go to sketch this line, thinking about it as a component of this system, I need to sketch it dashed. The points on this line do not solve that inequality, so they could not possibly be a part of the solution to the system. Okay, so here's my line with slope positive 1/2 and y-intercept positive 2. And I put him in dashed because he's got a strict inequality. The other one is negative 2x minus 1. So that is a line whose y-intercept is negative 1 and whose slope is negative 2. So the x-intercept here is not going to be an integer besides the point 0, negative 1. Can somebody tell me another point on this line? All right, in order to draw the line, I need 2 points. They don't have to be the intercepts. Just need 2 points. I know 1 point here from the y-intercept. Can you tell me another point that is on this blue line?
One, -3.
Excellent. 1, -3, right? The slope is -2. So if you go over 1, you're going to go down 1, 2. Or if you plug in x equals 1 here, you get y equals -3. Either way of thinking about it. Here's -2, here's -3, here's +1. So here's the second point that is on this line, 1, -3. So the line then, I draw this one dashed as well because strict inequality. Looks something like this. All right, you ready for the fast way to solve these, to shade the right region? This first guy, solved for y, says y is less than 1/2 x plus 2. The purple line here is all the points where y is equal to 1/2 x plus 2. So I'm looking for all the points at x comma y where the y value is smaller than the y value on this line. So the solution to the first inequality is all the shit below the purple line. Fast way to sketch solution to system. Y is less than 1/2 x plus 2. This is all the points below y equals 1/2 x plus 2. Why below? Well, because the y value tells you how high or low you are on the plane, right? That's the up-down coordinate. And we're saying the y values in the solution set to this inequality are smaller than the points on this line. So we're looking for all the y values that are below, right? We've got y is less than, that tells you want all the points below that line. So everything below the purple line solves the first inequality. The other guy, y is greater than -2x minus 1. This is all the points above the line y equals -2x minus 1. So I'm looking for all the points that are below the purple line and all the points that are above the blue line. So I will go in. And for everything below the purple line, don't want to clutter this too badly. I'm trying to shade lightly. It's hard to do with pen. And all the points that are above the blue line. So my solution region here is the overlap. It's this region. All this stuff. Fast, right? Simple, not bad. The thing is, when you are given a system that's not already in this form, in order to play this game, you need to put it in this form. And that might require some work with the inequality, right? Like solving for y, and you need to be careful. Remember, when you divide both sides of an inequality by a negative number, or multiply both sides of an inequality by a negative number, the inequality flips over. Besides that, inequalities, linear inequalities are the same as linear equations, solution-wise, like what you do with them. So yeah, this is the fast way to do it. Questions on this approach?
I have a question. So if we ever have to solve for y, would we run in a problem where we have to like switch the inequality sign if we're dividing by a negative?
Yeah, oh yeah, could totally happen. In fact, the last system we were playing with, if we wanted to do this, we would have to play that game. We would have to flip over the inequality when we solve for y. I can show you an example where we do it like that. If you're ever insecure or uncertain about the result, once you think you've identified your solution region, take a point that's in that region and plug it in and verify. It's like 1, 0 is right here. If I plug in 1 for x and 0 for y, do I get a true statement? Well, that would say 0 is less than 1/2 times 0 plus 2. In other words, 0 is less than 2. And if I plug in that same point, 1, 0 for the second inequality, x again is 1, y is 0, this would say 0 is greater than 2 times negative 2 times 1 minus 1. So 0 is greater than negative 3. That is again a true statement. So you can always use the second method to verify what you find. Or sorry, the first method to verify what you find with the second method. Let's look at one where we have to do what Tyson was asking about. Let's look at one where in order to play this game, you would have to solve for y. Are these all given to you, solve for y? We can play that game in just a second. All of the straight up ones here. Okay, no, here we go. All right. Oh, but those are all positive coefficient wise. Damn. Well, they have nerfed this considerably. It looks like there are not any systems here where you're actually going to run into that. Oh, yeah. Please tell me there's one in here somewhere. One second. All right, sorry about that. Well, yes, it is the case that you would have to be careful if you encounter that. It does. I don't see anything like that in your homework. So just for shits and giggles, let's go back to that previous system and see what that would look like. I'll just make up a new one. How about that? We'll do a fresh one. Okay. Oh, I did it again. Let's do this one greater than or equal to, and we'll do this one less than or equal to. Okay. So if we want to play the game that we did last time, we need to solve these inequalities for y. And when we solve the first inequality for y, because there's a negative here, we're going to have to be a little bit careful. So if I take 2x minus y is greater than or equal to -4, and I start solving this for y, first I subtract the 2x over, and that'll give me -y is greater than or equal to -4 minus 2x. And then when I get rid of that negative, I divide both sides by -1, the inequality is going to flip over, and I'll have +4 plus 2x. So this is all. That's the first inequality. The second inequality is x plus y is less than or equal to -2. And if I go to solve that for y, I get y is less than or equal to -2 minus x. So now if I sketch the two, this first guy I'm going to think of as, I'm going to draw the line y equals 4 plus 2x. That's a line with slope 4, or sorry, slope 2 and y-intercept 4. So here's 1 point on the line, and I know that if I were to walk to the left one, I would have to go down 1, 2. So the point -1, comma 2 is on there. That'll be my second point. So that line looks like this. And oops, I drew it dotted. This is a weak inequality, right? This is a less than or equal to. So I can actually go ahead and draw this one solid. The points on that line are a part of the solution set to that inequality. I'll do the same thing with the other guy. The other guy has a slope of -1 and a y-intercept of -2. And go down 1, 2. I'll also draw him solid. Slope -1 means he also goes through the point -2, comma -2. Do that as well. Yeah, well, okay. I draw both of these as solid lines because they're both weak inequalities, or equals to. And now I can think about the above and below thing. So this first guy says I want all the points that are below the line y equals 4x plus 2. Or sorry, 4 plus 2x. That's everything below the purple line. And this guy says I want all the points that are below y equals -2 minus x. So I'm looking for all the points that are below both lines. So being below the purple line means I'd be down here. Being below the blue line means I'd be down here. So the solution set is all of this stuff. Still quick, still not hard. But you do need to be careful when you solve that first inequality for y, making sure that when you get to this step where you divide by the -1, you flip over the inequality. Not bad, right? Any questions on what we did here? Okay, then before we go, let's take a look at least one little application problem. How are we doing for time? Oh, we're out of time, aren't we? All right, that's the basic of solving inequalities then. I guess we'll leave it here for now. Next time, we can talk a little bit more about solving systems of inequalities. There are a couple application problems here that are kind of fun, right? Like this one, where you have to think about a real world situation and come up with the appropriate set of inequalities. But that's not too hard. I think you guys can reason your way there. If you do get stuck on anything, of course, as always, you can come by office hours and talk to me. Make sure you're practicing the homework. Make sure you're keeping up with everything. If you have not done, please make sure you've done all the log and exponential homeworks as well. And in addition to that, the logarithm properties sheet that I posted to the announcements for our activity last week is a really good way to practice. So you've got lots of material, you've got the review packet for the final, you've got the log and inequalities thing, the log properties thing to work on, and in addition to the homework and the quizzes. If you need anything extended, if you're having a hard time with anything, please talk to me. Study hard, ask for help if you need it, and I will see you guys on Tuesday. Take care.